Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is computer number systems. Please follow me in this engineering lecture series by subscribing to my YouTube channel at https:/youtube.com/at Ndinechi Michael C. Like, share, and drop your comments in the comment section or reach out to me using my email addresses. You can also listen to my introductory lectures on computers in Module 006 if you go to my channel. You can also listen to other lectures I've made on computers in Module 014, Part 1 to 7 by going to my YouTube channel as stated. Like we said, we are going to look at computer number systems. So you know that digital computer circuits work with binary numbers and instructions coded in binary form. We also know that binary numbers contain only two different digits, zeros and ones. It is therefore very important that we develop an understanding of binary numbers, binary arithmetic, and instructions coded as binary patterns so that we can begin to comprehend how computers operate. The total number of different digits used in any number system is known as the base or radix of the system. When we talk of binary, which is base 2, we only have zeros and ones. When we talk of octal, base 8, we have from 0 to 7. When we talk of decimal, that is base 10, we have from 0 to 9. So, other numbers widely used in connection with computers and which are closely related to binary or to represent binary pattern are octal, that is base 8, decimal, base 10, and hexadecimal, base 16. In the binary number system, numbers are written as a sequence of ones and zeros. 0 in the binary system may be represented by a single zero or by multiple of zeros. Example, we can use 10 to represent 0. We can use 00 to represent 0. We can use 000. We can use 4 zeros. We can use 5, any number of zeros to represent 0. 1 in binary represents powers of 2. That is, if we say 2 raised to power 0 is 1, 2 raised to power 1 is 2, and so on, until we get to 2 raised to power any number, n. It is the position of a one-digit binary number that has the following meaning as illustrated. For instance, if we have 1111, if we look to the right, which we call the least significant bit, that one there represents 1 times 2 raised to power 0. The next one to it represents 1 times 2 raised to power 1, which is 2. The next one represents 1 times 2 raised to power 2, which is 4. The next one represents 1 times 2 raised to power 3, which is 8. If we go next, it becomes 1 times 2 raised to power 4, which will be 16. It continues like that to 32, 64, 128, and so on. So the binary number 1111 to base 2 is equal to decimal in base 10, 15, because the first one, which is the one to the right, called the least significant bit, is equal to 1 times 2 raised to power 0, which is 1. The one following is 1 times 2 raised to power 1, which is 2. The next one is 1 times 2 raised to power 2, which is 4. And the next one is 1 times 2 raised to power 3, which is 8, as seen there. So the right-hand bit is always referred to as the least significant bit, LSB, while the left-hand bit is the most significant bit. As we progress from right to left, successive bits increase their weighting value in powers of 2. Therefore, if, for instance, we consider a typical binary number written as 10101101 in base 2, the weighting will be as follows. The one to the right, which is the least significant bit, will be 2 raised to power 0. The following one is 2 raised to power 1. Continue until we get to the left one, which is the most significant bit. In this our case, we have string of 8 binary digits. So if you start from 0, then you will end in 7. So if we look at their equivalent, you see that 2 raised to power 0 is 1, 2 raised to power 1 is 2, 2 raised to power 2 is 4. If you continue, 2 raised to power 7 is 128. So if we put that binary number under them, that 10101101, you will see that it will give you, starting from the right, 1 times 2 raised to power 0, which is 1, and continue like that. Where 0 appears, you multiply by 0, it gives you 0. So that bit 10101101, what we just needed to do is, having known that from right going to the left is 1, the next one is 2, the next one is 4, the next one is 8, the next one is 16, the next one is 32, the next one is 64, the next one is 128. So if we arrange it like that and see wherever 0 is, we delete the decimal equivalent under it, you will see that you add up the remaining one, it gives you the equivalent of that binary number in base 10. So you don't need to do any arithmetic or any division or anything. You just have to know that there is a pattern from right to left: 1, 2, 4, 8, 16, 32, 64, 128, 256, and so on. Likewise, if you are going to work with binary fraction, we say that just as we use a decimal point to separate the whole and decimal fraction parts of a decimal number, we can use a binary point in binary numbers to separate the whole and fractional parts. The significance of the weighting of the bits behind the binary point is illustrated below. For instance, if we have a fraction of 0.1111 in base 2, the one to the right, which is now the least significant bit, will be 2 raised to power minus 4. The one following will be 2 raised to power minus 3, which is 1 over 8. The next one is 2 raised to power minus 2, which is 1 over 4. The next one is 2 raised to power minus 1, which is 1 over 2. So the equivalent of this 0.1111, if you work it out, will give you 0.9375. So just like we have done there, you see that for you to convert a number 0.1101, you see that the second digit from the right, which is 0, which translates to 0.125, multiplied by 0, cancels out. So you add the other ones, it gives you the decimal equivalent of that number. So likewise, you can do your conversion from decimal to binary. That's, we have known even from our secondary school. So, but just for rehearsal, say convert 18 to base 10 into binary, you do your division by 2 and put up the remainders on the right. Then from down up, you get what your answer will be. So decimal is not very much used in the conversion in computer system. We will see the reasons. As the ones that are commonly used are the octal and the hexadecimal numbers. So we say, digital computers handle binary ones and zeros with ease. We as humans find binary patterns difficult to handle. For this reason, octal base 8 and hexadecimal base 16 numbers are frequently employed. For more information on how to convert from binary to base 8, that is octal, or base 16 hexadecimal, I would like you to open the link below, the two links, because I've talked about it in those links. So repeating it here may not mean much for us. But the important thing is that when computer is making use of binary digits, it tries to group them to convey meaning. The first grouping is called the nibble, the next one is called the byte, and the next one is called the word length. So 3 terms concerning binary coded patterns are frequently used in computer terminology, namely nibbles, bytes, and word length. So nibble is a sequence of 4 bits. Anytime the computer groups 4 bits, the 4 bits grouped is known as a nibble. A group of 8 bits is known as a byte. So anytime computer groups 8 bits, it calls that a byte. Then the word length of bits, the word length is the number of bits used to convey data in a computer or microprocessor. So it can be 2 nibbles, which is 8 bits. It could be 2 bytes, which will be 16 bits. It could be 7 bits. As we can see, when we go down, when computer uses the ASCII code in form of 7 bits to represent any character. So we say binary patterns representing numbers and instructions are stored in the computer memory mainly. From there, it picks it to work. If you look at my previous lectures, which I gave the link, you will see how those bits are stored in the memory and the types of memory we have. So each binary pattern or the word consisting typically of 1 or 2 bytes. So when we say 1 byte, we are now talking of group of 8 bits. When we talk of 2 bytes, we are talking of group of 16 bits. So each binary pattern consisting typically of 1 or 2 bytes has its own location in the memory, and each location is given as an address quoted in hex numbers. Hex, we have said, is base 16. So please cool down and follow me in this illustration so that you get it well. We say, let us determine for a 1 byte computer which stores data in memory from address locations B000 16 to BFFF in base 16, the following. 1, the decimal equivalent for the first and the last addresses. Second, the amount of binary data in bits and bytes that can be stored in the memory space. Now, what we are doing is we are moving out from just seeing binary or computer number system as being converting from base 2 to base 10 or base 8 or base 16 and vice versa. We are trying to use it to see how it solves a real life computer problem. In the illustration we are talking about, we are saying that the first address in the memory is B000. And the question is asking us, what is the equivalent of this B000 in decimal? Because as human beings, we understand decimal better. And what is the decimal equivalent of the last address, which is BFFF? So let's go on. See, the first address, which is B000 in the 16, corresponds to the decimal equivalent of putting that number B000, the least significant bit, which is the right one, which is 0 now, is 0 times 10 times 16 raised to power 0, which is 0. The next one is 0 times 16 raised to power 1. The next one is 0 times 16 raised to power 2. The next one now is B. We have known that in hexadecimal, 11 represents B, or B represents 11, because we have to count up to 15 before going back to 0. So it becomes 11 times 16 raised to power 3, which gives you 45056 in base 10. So automatically, it means that in that computer memory that uses 1 byte, that the first memory location is 45,056 in decimal, in base 10. If we do the same for the final address, which is BFFF in base 16, you see that in hexadecimal, 15 represents F. So if we read the same, you see that the decimal equivalent will be 49,151 in the stem. So the question we are asked is one, the decimal equivalent for the first and the last addresses. So we have found the decimal equivalent of the first address, which is 45056, and the decimal equivalent of the last, which is 49151. So we go to the second question, which says the number of individual locations between B000 in the 16 and BFFF in the 16 will be the first one, this minus that. That is the last address minus the other one, which is 49151 minus 45056, which will give you 4096. Now, like in your statistics, because B00, the starting address is included, you add 1. So it becomes 4096. So now, so the total amount of data that can be stored will be equal to number of locations times number of bits per location. We have found that the number of bits per location from the question is 8, because we are told that it is a 1-byte computer. It is a 1-byte computer, meaning that the computer uses 8 bits to perform any action it is going to perform. Now, we found that the location is 4096 locations between the starting address, which is B000, and the final address, which is BFFF. So, in each of these addresses, it stores 8 bits. In other words, it will be, in number of bits, will be that 4096, which is the locations, times 8 bits. But because 8 bits equals 1 byte, it becomes also 4096 by 1 byte. So we say, note, the size of computer memory is often measured in units of 2 raised to power 10, which is regarded as 1 kilobits. 2 raised to power 10 is equal to 1024. Now, if you note the difference between conventional K, when you talk of 1000, you say 1K. But for the computer system, it has an extra 24. So when we talk of 1K in computing parlance, we are looking at 1024 and not just 1000. We are looking at 1024 and not just 1000. So we say it is important that you note this difference. Now, so the storage space between B000, the 16, and BFFF in the 16 is 4096 bytes, or 4 kilobytes. If you divide 4096 by 1024, it gives you 4. So you will now put it in kilobytes, because the second question wants us to know or to put it in form of kilobytes. And since the microprocessor has a word length of 1 byte, then the amount of information stored is 4 kilobytes, because 4K times 8 bits, which is 32 kilobits, if you change it to bits. Remember, there is a difference between bytes and bits. 8 bits makes 1 byte. So 4 kilobytes times 8 bits gives you 32 kilobits. So that is the amount of information stored. So why we put up this illustration is that at your level, we are not going to start asking you, people are not going to start asking you, convert this number from base 2 to base 16 or base 8, or convert from base 16 to base. You will be asked real life question on how computer manages the zeros and ones that are that it makes use of. Then, when you finish talking about converting zeros and ones, you go further to see how computers code these bits, and that is what we call the binary coded decimal. So, because of the everyday use of decimal numbers, it is very useful in many microprocessors and computer applications to code each decimal digit by an individual group of 4 bits or nibble. Such codes are referred to as binary coded decimal, normally abbreviated as BCD codes. BCD is a special form of binary code in which each decimal digit is expressed as a 4-bit pattern. A number of different BCD codes are in use. The most popular of them is the 8421 BCD code. In this 8421 BCD code, the most significant bit of the 4 bits is weighted 8, and the next 4, the next 2, and the least significant bit is weighted as 1, just like we've shown in the when we were starting, that the least significant bit is 2 raised to power 0, which is 1. The next one, 2 raised to power 1, which is 2, like that. So that is called the 8421 BCD code. And we said this code allows us to define uniquely any decimal digit by 4 bits. Note the distinction from the pure binary coding. Note also that 6 out of the possible 16 possible 4-bit binary groups are not used in BCD codes. And these are 1010, 1011, 1100, 1101, 1110, and 1111. We say that they are illegal in the 8421 BCD code. So I would like you to find out why these 6 combinations are not used in binary coded decimal. If you look at it, it has one pattern that is common. So I will want you to probably, in the comment section, put what you think, what you know, what you feel that is the reason why these 6 combinations are not being put into use in the 8421 BCD code. So again, indeed, there is another BCD code called the 2421 BCD code. In this case, the most significant bit has a weighting of 2, the next a weighting of 4, and the next a weighting of 2, and the least significant bit a weighting of 1. BCD codes having sign and weight are also in use. Remember, all this we have been talking, we have not mentioned about the sign of the numbers. So that will form the next thing we will talk about now. But again, there is also another BCD code known as the XS3 code. And so in this XS3, 3 raised to power 10, 3 to base 10, that's 3 in decimal, which is equivalent to 0011, are added to each 4-bit group of the 8421 bit. Take a look here. We see the decimal number to the left, the 8421 BCD code, which is what you have if you convert any of this decimal to base 2. Then you have the 2421 BCD code. In this 2421 BCD code, the least significant figure is having a weighting of 1, the next to the left a weighting of 2, the next a weighting of 4, and the last a weighting of 2. You see the difference with the other 8421 BCD code. So we will see one example. Then the XS3, we say that the 8421 BCD code is added 0011. So for 0, if you add 0011 to it, you have the equivalent in XS3. For 7, for instance, if you add 0011 to the BCD equivalent of that, you have what is there. If it is more than, you discard the carry. So you can easily find any of them. But mostly, the other two are not being used because of some difficulties and ambiguities. So let's see a quick illustration on the 2421 BCD code. So if we take decimal 5, for instance, which is given as 1011, which is given as 1011, decimal 5, which is given as 1011 in the 2421 BCD code. Now, see what the computer will do. We will look at the first one, give it weighting of 1, the next one weighting of 2, the next one weighting of 4, the next one weighting of 2. Now, that of 4 is 0. So what is remaining is 2 plus 2 plus 1 equals 5. So the 2421 BCD code, we always see 1011 as equal to 5 in decimal. But if you look at this logic it employs, it means that if you also have 0101, it will also sum up to decimal 5. So you see that in the 2421 BCD codes, it can only work for decimals 0, 1, 2, 8, and 9. And when it comes to 3, 4, 5, 6, and 7, it introduces some confusion. And that forms the main limitation of this 2421 BCD codes. Now, we have been talking of computers making use of numbers Now, if the computer wants to do some form of arithmetic that has positive or negative numbers, it means it will have to do something extra to be able to represent the sign of the number it is working with. So that leads us to the positive and negative numbers in binary. So we have been talking of unsigned binary, and it is the most basic form of number representation. In unsigned binary, all numbers are assumed to be positive, and the ones carry the appropriate power of two weightings, as we have discussed previously. Although for some applications, simple unsigned binary is adequate, in almost all computer applications where arithmetic operations are involved, there is need to represent positive and negative numbers and produce the correct sign bit. Take for example, this table shows unsigned binary. In the unsigned binary, if we have a binary digit 10000000, if you convert it, it gives you 128 raised to 128 to base 10. That is 128 in decimal. The second one, if you look at it 00, it gives you 0. The third one, if you look at it and convert, it will give you 255 in base 10. The other one will give you 51 in base 10, because we are not talking of any sign. So we say it's an unsigned binary number. So we say the simplest form of signed binary representation is where the most significant bit indicates the sign of the number. The bit is reserved not to denote any numerical value, but simply to indicate the positive and negative sign of the number. In this signed binary, the most significant bit, MSB, is set to 0 to indicate a positive number, while all the other bits indicate the magnitude of the number in the normal way. And this is called the signed and magnitude convention. Look at this table as an example. In the table we have seen, we still saw 10000000, and we say that when you have that in the sign and magnitude number, it represents 0, because the one you are seeing there is used to represent the sign of that number. If you look at the second one, we said 0 as the most significant bit is used to represent that the number is a positive number. The first one is minus 0, because the most significant bit is 1, but because we don't normally put minus 0, that is why it is 0. So if you look at the third one, you see 1111111. In the unsigned, look at the unsigned, that equivalent of 11111 into 8 places is equal to 255 in base 10. But in the signed, you look at it, you see that it is equal to minus 127 in base 10, because that most significant bit has been used as sign, which represents minus sign. If you look at the next one, they are the same, except the most significant bit. So for most significant bit 0, it gives 51 to base 10, while here, when it is 1, it gives minus 51 to base 10. So we can quickly do another exercise. Please confirm that you understand this exercise. Let us determine for the general case the number range that can be accommodated in an n-bit register using unsigned binary and using sign and magnitude binary. So for unsigned binary, all the n bits are used to represent numerical information. Therefore, the total number of different 1-0 combinations that can be obtained with n bits is 2 raised to power n. Hence, 2 raised to power n numbers from 0 to the maximum number. So the maximum will be n max equals to 2 raised to power n minus 1. If we use 8 bits, remember we start from 0. So the maximum number will be 2 raised to power 7, meaning 2 raised to power 8 minus 1. Let's go back a bit to see it. Look at the example of the unsigned bit. If you look at the first one, we have 8 bits. The maximum we could represent is 2 raised to power 8 minus 1, which is 2 raised to power 7. So in the sign magnitude representation, the most significant bit is used to denote the sign of the number. So it will give n minus 1. Like we have seen, we have 8 bits. So we minus the most significant one. It gives you n minus 1. But then, because the 0 is there, you have the maximum positive and negative numbers to be equal to 2 raised to power n minus 1 minus 1. Let us look at this table. You see the maximum number here for the sign and magnitude is 2 raised to power 6, even though we have 8 bits. So that's, guess that. So you can also try to do this to determine the maximum positive and negative numbers that can be held in the register of an 8-bit general purpose computer employing sign and magnitude binary numbers. You can take that out and drop your answer in the comment section. I will go through, and for people that didn't get it right, I will put them right. Then we continue. We have said that in the sign and magnitude, the most significant bit, when it is 0, it becomes a positive number. When it is 1, it becomes a negative number. So we say, unfortunately, the sign and magnitude representation still has some limitations. It is not possible to perform the basic arithmetic operations with positive and negative numbers and automatically provide the correct sign for the results. So for you to be able to do that, you have to do something in addition. That thing the computer does in addition is called the ones and twos complement. So for this reason, two's complement representation for signed binary numbers is preferred, which can automatically produce the correct sign for arithmetic operations. As for the sign and magnitude, the most significant bit of the number is used as a sign bit. We say that MSB is 0 for positive numbers, and all other bits are used to represent the magnitude in the normal binary way. For negative numbers, the number is first converted into its two's complement form. I want you to note this, very important. When a number is given as a negative number, you must first convert that number into its two's equivalent, two's complement equivalent. How do you do that? You obtain this by following a very simple rule. That rule is 1. The positive binary number, that is the number of the same magnitude as the negative number, is first inverted or complemented. That is, you change all zeros to ones and all ones to zeros. This gives you what is known as the ones complement representation of the negative number. Then you increment it. That is, you add 1 to the least significant bit of the result of the ones complement. This now gives you the two's complement for the negative number. If there is a fractional part, then the one you will add must be added to the furthest right-hand bit behind the binary point. Let's take, for example, say find the two's complement representation of minus 127 in base 10. Now, what you do is you first convert this positive number equivalent of 127 to its binary equivalent. You see, we have to say plus 127 because the first step is to convert the positive equivalent of that number. So if we do that, we have 1111111. Then because this is positive 127, we add a 0 to the leftmost end to show that the number we are looking at is a positive number. That is what the first step told us. Then we complement by changing all zeros to ones and all ones to zeros. So that's, if we do, it gives us 1000000. Then we add 1 to the least significant bit, and it gives us 1000001. So note that after complementation, the most significant bit automatically becomes a 1, indicating a negative number. Now, we bring it down to something like arithmetic. Say we want to determine 15 in decimal minus 9 in decimal. Without being told, we know that the answer is 6. But it is not straightforward for a computer to just find that the answer is 6. It has to do some processes. And say, first, we know that 9 is possessing a minus sign. So we find the 2's complement of it. How do we do that? Step 1, we find the positive equivalent of 9 in decimal, which is 1001. Step 2, we say we append a 0 to take care of the positive sign, because we want to make this 9 look like a positive number, so that it will be 15 plus whatever. Now, this gives us 01001, because 9 is 1001. We append 0, which represents the sign positive. So step 3, we invert all zeros and all ones. This now gives us 10110. We call it the ones complement. And step 4, we add 1 to the least significant bit. This gives us now 10111. Then we add the two numbers. So we note also that 15 in base 10 is 1111, and we append a 0 to indicate a positive number. This gives us 01111. So we add the 2. If we add the 2, it gives us 10100110. It is more than the bit, so you see that there is a carry on the left. You neglect the carry. Automatically, the computer gives you your answer as 00110, which is plus 6 in real life. Quickly, let's do the reverse of that. The computer is now looking at to solve minus 15 in base 10 plus 9 in base 10. Just like before, we know that 15 is possessing a minus sign. So we find the 2's complement of it. Step 1, we find the positive equivalent of 15, which is 1111. Step 2, we append a 0 to take care of this positive sign for 15, which gives us 01111. Then step 3, we invert all to convert to one's complement, which gives us 10000. And step 4, we add 1 to the least significant bit, which gives us 10001. Then we add the two numbers. When we added the two numbers, it will give us 11010. So automatically, the last, which is the most significant bit, is a 1, showing that the number we have is a negative number. Our result is a negative number. That is the indication of that 1 at the most significant bit. So since the sign bit is a 1, it means that the true difference is negative. Therefore, the magnitude of the difference is the 2's complement of 11010. To find the 2's complement of 11010, we invert all the zeros to 1 and all the ones to 0. This gives 00101. Then we add 1 to the least significant bit. This gives us 00110, which is 6 in base 10. Because the sign is already determined to be a negative, then the answer becomes minus 6 in base 10. So I want you to show me how far you understood these 2's complement, how the computer does that by trying to do this example for me. Minus 22 in base 10 minus 79 in base 10. We already know what the answer will be in decimal, but we want you to follow how computer will do it to be able to achieve the result. I will go through the comment section and see people that we got it right and commend them. People that didn't, I will also correct them. So try and do that and put your answer in the comment section. Now, the computer doesn't stop at that point. You see, it continues to improve, and that is what we are following until we get to the final point that computer makes use of this binary to solve any logical problem, any arithmetic problem, any differential problem, no matter what the problem is, the computer solves that by manipulating zeros and ones. So the next we are going to see is the fixed point and the floating point numbers. The term fixed point is used to indicate that the binary point is fixed at a position where the power of the base 2 weightings changes from positive to negative. That is, at the point between 2 raised to power 0 and 2 raised to power minus 1 bit. Fixed point notation has two major disadvantages. One, the number of digits or bits used restricts the range of numbers that can be represented. And two, in carrying out calculations involving fractional parts, it is necessary for the arithmetic logic unit circuit to keep track of the binary point so that it can be correctly positioned in the final result. So this increases cost in additional circuitry in processing time. Below is an illustration of how a typical number can be represented in a fixed point notation. Take for instance, we want to represent a decimal number minus 58.97. You see, the computer will have 1, 2, 3, 4, 5, 6, 7 neighbors to do that. Neighbor set of 4 bits. The first most significant 4 bits, it will use to indicate the number of digits. If you look at the test case we are looking at, 58.97. So we have 4 digits. The computer places binary 4, equivalent of 4 in that most significant bit. The next neighbor, which is the next 4 bits, will indicate the position of the binary point. The binary point is to 2 decimal places. You see, it puts binary equivalent of 2. The next one is to indicate the sign. In our case, it is minus 58, and they say that in signed numbers, the computer uses a 1 to indicate minus. So it puts a 1 there, and then because it is 4 digits, the first digit is the most significant digit is 5. It puts equivalent of 5 there. The next one is 8. The next one is 9. The next one is 7. So immediately it sees this, you'll be able to look at this fixed point and give exactly what the answer is. So we are saying also you can, take home this and do this assignment and see how do you represent 9, 4, 8.39 using fixed point notation, 8.765, 4166.984, and 207.0. Just try to, do that and represent these numbers using fixed point notation. Then floating point representation, which is another way, has the advantages of being able to accommodate a much wider range of numbers for a given number of bits than fixed point. Remember, we said the fixed point has two major disadvantages. The floating point tries to overcome that to allow you to represent any number. So say floating point numbers in decimal are very widely used. For instance, you have 6,291,000. Floating point equivalent will be 6.291 times 10 raised to power 6 or 0.6291 times 10 raised to power 7. In binary, it will do the same. In fraction, it will do the same. So it has a general format which is n equals mb raised to power e, where e is the exponent, m is the mantissa, and b is the base. Then, a typical illustration of a floating point number using 32 bits of 4 bytes is as shown. The computer divides the 4 bytes into 4 places not of equal bits. So the first byte, it uses the most significant bit of to show the sign. So we call it S. If you look at the arrow, you see that it uses 1 byte for exponent. The next one is the exponent. The next one is the sign bit for M. And the next one is the mantissa representing the number you really want. Now, if you look at this very well, you see that it says that the computer uses 1 byte, which is 8 bits, for the exponent. And the first bit there stands for the sign bit of the exponent. Is it raised to power -8 or raised to power 8? It has to represent the sign of that exponent. And it is 1 byte, meaning 8 bits. In other words, immediately you remove 1, what will remain will be 7 bits. 1, 2, 3, 4, 5, 6, 7. So 11111 raised to power 2 is equal to 127 in decimal. In other words, the computer that is using 4 bytes for each floating point number cannot do any mathematics that has anything more than raised to power 127. That is why you have some calculators, if you raise anything raised to power more than 127, it gives you error because it is limited to 4 bytes or 32 bits. But we know that some digital systems now make use of 64 bits, some 128, and they can do now higher exponent computation. So you see the essence, the real life application of this floating point arithmetic. So, and finally, coming to the end, we have what we call the alphanumeric codes. Many digital systems, and particularly digital computers, are capable of handling alphabetical characters and special characters you will normally see in the keyboard, in addition to numerical data and control information. So digital systems, as we already know, work entirely with binary digits, that is ones and zero digital signals. This signal being a two-state electrical pulse strength that represent the binary data where the voltage can take only one or two voltage levels. One of the most commonly used binary codes for information interchange between microprocessors, digital communication links, and data processing systems is the ASCII code. By ASCII, the full explanation is American Standard Code for Information Interchange. This code employs 7 bits and therefore can only do 2 raised to power 7 or 128 different character code. Extra bits may be added to each of the 7-bit character to indicate start or stop and for parity check. As we go on, we'll be able to see also what we mean by parity check in more detail. But for now, the parity bit is usually added to give an indication of whether or not an error has occurred in the transmission. By this alphanumeric codes we're talking about, by the time computer finish doing all these manipulations of zeros and ones, it may have to transmit it to somewhere else. In the process of transmitting it, it has to employ another form of code, and that is what we call the alphanumeric codes. Each one of them is the ASCII code, and this ASCII code makes use of 7 bits instead of 8. So it doesn't make use of byte. It makes use of 7 bits, which is 1 bit short of the byte. And we say that that 1 bit is now used for some other things like start, stop, and parity checking. The parity bit is appended to each 7-bit character so that the total number of ones is either even or odd. When odd parity error detection is employed, the parity bit is 0 if the total number of ones in the 7-bit character is odd. In other words, if you are transmitting a binary string, the system checks the number of ones in that string you are transmitting. Say that if the total number in the 7-bit is odd, you know what odd number is, then it will append 0 as the 8th bit to show that the number of binary ones in that transmission is odd number. If at the receiving end, the receiver receives a corrupted signal and the odd number, the number of ones is not odd, the system automatically knows that an error has occurred. It will find where that error has occurred and correct it. And you say that your system is automatically doing error detection and correction. If you follow us in our future lectures, which we'll be doing in the next 1 week or two, even though it is not purely in computing, it is in communications. We will see how the system can detect that error, the bit that is in error, using this parity check and correct it. Because if it detects that the bit that is in error is a 0, on its own, it changes it to 1. And by the time it changes it to 1, it becomes correct. So you say that your system is being able to do error detection and correction. So if the number of ones is even, then the parity bit is 1. For even parity, the parity bit is such as to make the total number of ones in all characters even. The ASCII code is now very widely employed and is virtually the international standard for data communication and storage. Another alphanumeric code developed by IBM is the extended binary coded decimal interchange code. This code uses 8 bits per character together with the control signal. The four least significant bits define a group of 16 characters, while the four most significant bits qualify a particular group within the code. So, thank you for making our time to listen. Please share the lecture with friends who may not be able to join in the live lectures. Give your comments, like or dislike the lectures, but more importantly, put up your comments, your questions in the comment section. I will go through the comment section and put everybody through where they are making mistake. Put up your questions, they will be answered. Thank you for listening.